This is part 3 of Structural Mechanics 3. We are going to answer some questions, and I want you to give yourself a number. So if, for example, your number is 652,171, then the sum of the digits of this number are 6 plus 5 plus 2 plus 4 plus 7 plus 1, which is equals to 25. So your unique student constant is now following this formula here will be your student number divided by 10 to the power 5 plus sum of your student number, that is SU, over 10. Now the formula now will be now this one all over 10 to the power 5 over now this one over 10. Now my student constant will be now this one to 4 significant figures. So this will be important when you're answering these questions. So I have question number 1. I have these questions and answers, and I want us to go through this together. Now the figure Q1 shows a pin joint spring bar system consisting of 3 identical rigid bars of length L over 3 that are strengthened by 3 torsional springs at the joint A, B, and D, with stiffness constant of KL squared, 2KL squared, and now your student constant multiplied by KL squared respectively. The middle bar is further supported at the middle point C by a linear spring with a stiffness constant K. A vertical load P is applied at the joint A, where the lateral movement is fully restrained. Now, I hope you have understood the description, and it is as follows. You can see the figure Q1. Now let's get to question number A. State the 2 independent displacements that you will use to describe the unstable deformed configuration of the system. Then express the lateral displacement at C and the vertical displacement at A, also in terms of these 2 displacements. State the 2 independent displacements that you will use to describe the unstable deformed configuration of the system. Then express the lateral displacement at C and the vertical displacement at A, also in terms of these 2 displacements. 4 marks. Now, let's say my number my student number is 964,354. Now, the sum of this 9 plus 6 plus 4 plus 3 plus 5 plus 4 is total of 31. Now, my student constant will be now that one over 10 to the power 5 plus 31 into 10. It will be this into 10 to the power 5 plus this into 10. Now it will be log. Okay, log to base 10. Log to base 10, that one now. Now I find my answer is 1.105. So question A. Our question A, this one, the answer is assume the following displaced configures are based on the 2 independent displacements. So assume D1 and D2. Okay, so this one is displaced as followed. Now you can see beta here, theta here, alpha here, and then phi at this point. These are the angles. Then you can see the spring here. Now this spring is pushing this toward this side. Now this one has displacement d1 which is greater than d2 as you can see, and as this load is also pushing this point load, pushing this point downward. So that is the answer to question A. Now, lateral displacement at C should be equals to, if you can go back to, now lateral displacement at C. C is which point? Now lateral displacement at this point, which is at the center, it is at the middle of B and D. So it's the midpoint. It should be now d1 plus d2 over 2. Now assume small displacement. Hence, beta will be d1 over L over 3, which should be equals to 3 d1 over L. Alpha will be equals to d1 minus d2 over L over 3. Now it will be 3 d1 minus 3 d2 over L. Phi will be equals to d2 over L over 3. That is 3 over d2 over L. Now theta will be equals to beta plus alpha. Now it will be equals to this one will be equals to this plus this as shown here. Again, theta 1 should be equals to now 6 d1 minus 3 d2 over L. Now theta 2 will be equals to phi minus alpha. Now that is this one minus this should be equals to also 6 d2 minus 3 d1. Now the vertical displacement at A u will be equals to now L over 3 minus L cos B. Okay. Now where we get L cos B? You know the Pythagoras theorem and the triangular formulas. So that is cos, tan, and sine. So that one cannot confuse you there. So now this one will be L over 3 cos beta plus L into L over 3 minus L over 3 into cos alpha plus L over 3 minus L over 3 cos phi. Now u will be equals to, if you do the substitution, L over 3 into 1 minus cos beta plus L, now 1 minus cos alpha, again 1 minus cos phi. So under small displacement, cos x should be equals to 1 into subtract x squared over 2. Now 1 over cos x should be equals to, this one should be equals to x squared over 2. Now u, the displacement, will be equals to now, if you do the substitution here, now you'll get L over 3 into angle beta squared over 2 plus L over 3 into angle alpha squared over 2 plus L over 3 into angle phi squared over 2. Now if you do the substitution, you will arrive at vertical displacement at A should be equals to u is equals to 3L into d1 squared minus d1 plus d1 times d2 plus d1 squared. Question number 2. Now derive the total potential energy TPE as the function of the two independent displacement. Now internal energy should be equals to U is equals to half K L squared multiplied by beta squared plus now I have now based on the formulas we derived up here, um, 2L squared multiplied by angle beta squared plus half into um, now the constant, the student constant, which we found to be 1 point. Now this one is based on here, this our stiffness constants, okay, plus half k d1 plus d2 over 2 into bracket all of that squared. Now you expand and then simplify the algebraic equation. Now you arrive at the displacement is equals to 0.5525 k into bracket 6d2 minus 3d1 into bracket square plus 325 k d1 square minus 286 k d1 times d2 plus 73 k d1 square over 8. Again, if you simplify further, you'll get that total potential energy, which now the external energy V is equals to negative P, now which is the force multiplied by the displacement. Now which will be equals to this one 3P over L multiplied by that is negative. Don't forget the negative sign. Now the total potential energy should be equals to U plus V. Now it will be equals to this one plus now negative, this one now will be subtract this one. Now this is the answer. Now calculate the two critical values of the applied load P at which equilibrium becomes unstable. So calculate the two critical values of the applied load P at which equilibrium becomes unstable. For equilibrium, d theta over d1, that is the derivative of theta over derivative of d1 should be equals to 0. Also, derivative of theta into derivative of d2 should be equals to 0. Now, if we do the derivative of this one in terms of d1, you will get that the answer is that one. If you derive this theta in terms of d1, okay, the derivative of theta in terms of d1. Now, if you derive this one in terms of d1, of course, you know derivation and integration. Okay, this is derivation. You derive. Okay, it's not integrate, derive. Of course, you place these two. These two comes here. Okay, two comes here, and then now this one becomes 1. So now we have derived in terms of d 1. Okay, again here this come toward this side, you will remain with this answer. So after deriving and simplifying, you will come into this answer and then arrange in matrix form. Then you get the answer to be 91.195k minus 6p over L into bracket, then into bracket minus 55.64k plus 3p over L d1. Okay, and this is over again. This is the way the matrix looks like, multiplied by d1 d2, which should be equals to 0 0. Now for an untrivial solution, the determinant of the stiffness matrix must be equal to 0, right? So this must be equal to 0. Now after you simplify and solve this quadratic equation, you get this quadrilateral equation. Now apply the quadrilateral equation formula. You get that P should be equals to 561.51 plus 259.6437 over 54. Now and this is the second answer, and this is the first answer, right, of this quadrilateral equation. Now this becomes 5.2231 KL, and then P2 is 15.7536 KL. Now you follow that formula. This formula, I suppose we covered this in part 2 and part 1. Now determine and schedule the corresponding unstable deformation mode of the system. Now the buckling P1 is this one. So substituting into our matrix and then making those linear equations, you will get that d2 is equals to 1.4975 d1, and v1 is equals to 1 and 1.475. Okay, now the buckling mode 2, substitute now P2. Now you arrive at negative 0.2519 d1. Now V2 is 1 and the answer here. Now sketch of the corresponding deformation is as shown in the diagram. Question number 2. Figure Q2A. Now this figure with this dimension, that is h is equal to 0.2 meters, b is equal to 0.12, t is equal to 0.02, and b2 is equal to 0.1 meter. Now A here, let's continue. Shows approved cantilever beam structure of 5 meter that is subjected to 2-point load at positions shown. This 2-point load, right? The frame has a uniform non-standard Z shape. Cross section as illustrated in figure Q2B. Assume that the yield stress of the frame, that is stress Y, is equals to 350 MPa. Now compute the second moment of inertia of the cross section, that is the I section. So to determine the second moment of inertia, split the cross section up into separate shapes. Now you can see this diagram drawn here, sketch, and then dimensions. Construct a table to determine the position of the cross section in the vertical direction. Now area 1, y a is equals to that. Now the area is equals to that a y. Area 2, now this one is area 1. Okay, this one is area 2, this one is area 3. The area in meter squared is 4.42 times 10 power 3, that is in meters. So the area is equals to, of course, 0.0221 multiplied by 0.2. Okay, so you arrive at this answer. Now the first area is 0.12 multiplied by 0.02. You arrive at 2.4 times 10 power 3. Now the y, that is the cross-section centroid, construct a table. Now the position of the cross-section centroid in the vertical y direction, all right, is at 0.23, now 0.12, 0.12, okay, and then here will be, of course, 0.01, 0.01, that for area 3. So the um, 0.01, now this one divided by 2, and this one um, is, so y is the vertical distance from cross-section base to centroid of individual area. So the vertical distance from cross-section base to centroid of individual area. The cross-section base is this point, all right? This is the base. Now, the area 3, the midpoint is 0.01. Now, the distance from the base is 0.01. Now, question number 2, the centroid is at 0.1. Now, from the base, 0.1. Now, from the base, it will be 0.12. This one, it is 0.01. Now, from the base will be 0.01 plus 0.2 plus 0.2. Now, that one will be 0.23, right? 0.23, as you can see. Now, area A is equals to area. Now, AY will be now the moment. Now, the position of cross-section centroid is as seen, AY over A. Now, the centroid of the entire cross-section will be now the total of this, summation of this over the summation of this, the 0.0125 meters. Now, second moment of inertia will be given with the summation of that formula, where I is the second moment of inertia of individual shape which form the overall cross-section, A is the area of individual shapes which form the overall cross-section, and D is the vertical distance between the center of individual shape and the center of overall cross-section. Now, substituting into this, you get now, I is equals to this formula, BD cubic over 12, okay? Now for each shape, you get the answers as follow. Then you do the summation of area 1, area 2, and area 3. Okay, then get the answer is as shown in the diagram. Now, we are in question number B. Determine the elastic modulus and the yield moment of the cross-section. So yield moment of the cross-section, My, is equal to stress multiplied by moment of inertia over Y maximum. So Y max is equals to is given by that formula. If you simplify, you get the answer is 0.1255, right? So yield stress of the frame is given by 350 MPa. That is 350 times 10 times times A, which is given by that So My is equals to 89 kilonewton meter. Now elastic modulus of cross section ZE is equals to Mi over stress Y. Now this is equals to 189 over 350 times 10 power 3, which now is equals to 5.4106 multiplied by 10 power negative 4 meter cubic. Determine the plastic modulus and the plastic moment of cross section. That is just 2 marks. So in order to determine the plastic moment and plastic modulus of cross section, first the position of the area axis EAA need to be computed. Now at the top it's given as shown. At bottom is given as follows. Now 0.1 multiplied by 0.2 plus 0.221 multiplied by 0.2 minus YE. Now for equal, A top should be equals to A at the bottom. Now if you do the quadratic equation, the algebraic equation there, you get that Y is equals to 90 times 10 power negative 3 meters. Now side view is as follows. F1 is equals to A multiplied by stress in Y, which is equals to 0.12 multiplied by 0.02 multiplied by stress in Y. Now substituting and simplifying, you get that the answer is F2 is equals to 199 times 10 to the power negative 3. F3 now is 2.4299 times 10 to the power negative 3. F4 now is 2 multiplied by 10 to the power negative 3. Now H1 is given by that formula. Now if you substitute and then use this formula for plastic moment, you will get that MP is equals to 246.135 kilonewton per meter. Now ZP is equals to 7.031 times 10 power negative 4 meters. Calculate the shape factor of the cross section. So shape factor alpha is equals to ZP over ZE, which is equals to now 7.0321 multiplied by 10 to the power negative 4 over 5.41606 times 10 to the power negative 4, which is equals to 1.2997. Now use the static or mixed method to find the critical value of P that causes the plastic collapse of the frame when A is equals to 2 meters. We start by static method. You need to determine the bending moment Bm diagram of the structure and the degree of indeterminacy, where I is equals to R minus 3n, which is equals to 4 minus 3 times 1, which is equals to 1. So need to split the structure up. So you can see the diagram as follows. Now E summation is equals to 0. Now this one should be equals to 0. Now doing the algebraic equation, you get that V D is equals to 1.242P. Now MC should be equals to 0, which is equals to negative Bm plus Vd. You get that Bm at C is equals to 1.242P. Now summation of MB is equals to 0, which is equals to negative Bm minus P times 2 plus 3 Vd. Now Bm is equals to negative 2P plus 3 into 1.242P. Now Bm is equals to negative 2P plus 3.726P. Now Bm at B is equals to 1.726P. Now this is as shown in this diagram. Now moment combination diagram is BMD1 plus BMD2. Now following from the inspection of the bending moment diagram above, assume a plastic hinge at B. Now you get that 1.726P minus 3MP over 5 is equals to MP. Now 1.726P is equals to 8MP over 5. Now P1 is equals to 0.927MP. Now, check, assume the plastic inch at C instead of, and compare the resultant P value. Now, after substituting this formula, we get that the P critical is equals to 28.1565 kilonewton. Now, assume that A is changeable. Using a try and error method, determine the critical position A with an accuracy of 0.1 meter that results in smallest plastic collapse load P. Now, assume that A is changeable. Use a try and error method. Determine the critical position A with an accuracy of 0.1 meter that results in the smallest plastic collapse load P. Now, distance A is now changeable. Need to determine the critical value of that results in the smallest plastic load P, as you can see in the diagram. Now, M is equals to 0, which should be equals to negative 1.105 P times A minus 4P plus 5 VD. Now, VD should be equals, after doing substitution and simplification, 0.221 PA plus 0.8 P. Now, MC is equals to that. Now, simplifying and doing the algebraic equation, we get the answer. Bm at B is equals to 0.305 Pa minus 0.221 Pa squared. Now, assume as plastic hinge will develop at B, which is dependent on the value of A. Now, we get that 1.305 Pa minus 0.221 Pa squared minus MP 1 minus A over 5 across the bracket, and then is equals to MP. Solve for P. After solving and simplifying this equation, we get that P at A is equals to 200 MP minus 200 MPa into A into closing opening parenthesis that 1305 minus 221A close the bracket. Now use a trial and error to determine the critical value A that will result in smallest plastic collapse P. Is it worth noting that A must lie within the range of 0 and 4. Try 0.1. Then get the answer is that. Try 1 meter, you get the answer is that. Now try 2 meters, you get the answer is this. Same value that was computed in part E. Now try 3, you get the answer is that. Try 4, you get the answer is that. Now critical lies at A is equals to 3 and A is equals to 4, because they have the smallest values. So try 3.5. Now try 3.6. Now try 3.7. So the critical value is 3.6 within an accuracy of 0.1 meters. Of course, you can see the value is going down, then start to rise again. So now this is our critical value, because you can see this value is going down, then rising. Okay, so we know that the critical position is linear, because it's still going down, then start to rise. So it's go down to 3.5, you get that, get this, then it rise again by 0.1. So this one is our critical value, that is 3.6 meters. Now this will be the end of this video. There are 2 more questions which we will answer in our next video. If you like this video, please consider subscribe my YouTube channel. Thanks.